heat into gas is 80,000. Change in its internal energy is equal to 46,142.7. Work by gas, we don't know. And then subtract that. So 83,857.3. Okay? Notice the work that the gas had done before, 35,000. You see that? 35,000. Over here, the work done by the gas is only 33,000. It does less work because the area under this graph is less. Okay? Now here's an interesting thing we can do. We can make a whole cycle out of this. We can, for example, go like this, go up, and then go back, isobarically. Or we could go this way, go down, and go back. Either way. Well, let's actually do that. That'd be more interesting. Let's go forward isobarically, go down, and then go back up. Well, we made an engine out of this, a whole cycle, right? We made a whole cycle out of it. We go forward isobarically, we go down isovolumically, and we go across this way. Okay? What would be the total work done by the gas in that whole path? Okay? This one, because forward it does that much work. Going back it does negative this work, right? So you take the difference of the two, that gives you the area under this graph. So what would that be? 35,285.45. This 33,857.3. So during that total path, the work done would be 1,428.15 joules. Okay? How much heat would have come in during that whole process? Well, during the forward process, how much heat comes in? This one, 88,213.62. 88,213.62 joules. Right? Because we already have that. On the way back, what happens? Well, since we're going reverse direction, how much heat comes out? 80,000 joules is dumped by the engine. It comes out of the system. Right? So it's going to be heat out 80,000 joules. Okay? Now, during the isovolumic process, what's happening? As you're going from this volume to this volume, well, let's find out actually. What's happening from here to here? Well, its temperature here, when it's at this corner, is what? That one was temperature of 454 Celsius, right? At that corner. What's the temperature over here? Okay, from here to here. Well, we know that when it ended here, its temperature was 400 Celsius. That was given in the problem. It was 400 Celsius. Okay? So if you go from 454 to 400, what's the change in internal energy? So delta E is equal to 3 halves nR delta T. So delta E is equal to 3 halves times 10 times 8.314. And delta T, remember, I could do it in Celsius. So I could do the final temperature, which is 400, minus the initial temperature, 454.41. Well, this one's going to be negative 54.41 Celsius, right? So you're actually cooling down. What is going to be the change in internal energy of the isovolumic process? So you have 1.5 times 10. So negative 6,785.47 joules. So we could put that here. Negative 6785.47. So what's going to be the heat that comes out of the system or goes into the system? Well, for isovolumic process, whenever the gas is going vertically down or up, the work done by the gas is 0, right? So work by gas is 0. So the only thing you have is heat into gas is equal to change in internal energy of gas for isovolumic process. So now, since the change in internal energy is negative 6,785, the heat into gas is the same. Negative 6785.47. Well, what does that mean? If a negative heat went into the gas, that means the heat came out of the gas. So we can say heat out of gas is equal to positive 6,785.47 Celsius, right? So therefore, heat is coming out of the system here. 6,785.47 joules is coming out. So, we know from the conservation of energy that the heat that comes in, the heat that you extract from the hot reservoir must be equal to the work done by gas, or in this case it's acting like an engine, so work done by the engine, plus the heat that it dumps into the cold reservoir. So how much heat is coming in? 88,213.62. How much work is the gas doing? Well, we have written that here, okay, 1,428.15. 28.15. So here's a way that you can check to see if you've done the whole cycle correctly. You add up all the heat that you dumped to the cold reservoir. So how much did you dump here? So Q cold, you basically have what? Well, you have the heat that you dumped here, 80,000. And then we found out that during this process, 6,785.47 joules were dumped during the isovolumic process. So if I add this and add this and add that, it should give me this. Let's try that. 1,428.13.62 perfectly comes out. Okay, so energy is conserved. What's the efficiency of this engine? Efficiency is defined as 100% times how much work the engine does divided by how much heat you need to run the engine, right? Okay, how much work did the engine do during the whole cycle? Not much, right? So you did, the engine did 1,428.15 joules of work. How much efficiency is that? 1,428.15 divided by 88,213.62. That's going to be, multiply that by 100, 1.6% efficiency. So not very efficient, okay? Because the major reason is because there isn't too much temperature difference between 454 and 400. It starts at 30, goes to 454, and goes down to 400, and then goes back to 30, right? So what's the highest efficiency that this machine can have if you run it between these two temperatures? Okay? What's the highest efficiency? The equation is 1 minus T cold over T hot. That's known as the Carnot efficiency. The Carnot efficiency is the highest efficiency an engine can have running between two extreme temperatures, right? So what are the two extreme temperatures that this whole engine cycle is working on? Well, the whole engine is working through a cycle. It's starting at 30 Celsius. The highest temperature is 454. Then it goes to 400, then it goes back, okay? But I could have gone back different way. I could have gone even more down and then go back. Even more down, go back. I could go back isothermally, okay? So that would be a topic that I would do more in an advanced level, because for isothermal, we need to know how to take the integral under the graph. So if I go back isothermally, I would go all the way down to 30. Then I would go back isothermally, I could do more work, right? So I will do that kind of problem later on when I do a more Physics 2 lectures. Okay, we will get to that eventually. But for this one, I only went to 400, then I went back to 30, right? So the highest efficiency I could have is going to be 100% times 1 minus, what's my T cold? The coldest is 330 Celsius, which in Kelvin is 303. What's the highest temperature in Kelvin? 727 in Kelvin. 727.56. So let's take the ratio of that. Okay. So the final conclusion, therefore, is that if I had taken a different path, I had gone straight, went down, and went back isothermally, the area under the graph would have been bigger. My efficiency would be closer to the ideal efficiency of 58%. It wouldn't necessarily equal 58%. It's still going to be less, but it would be closer to the ideal Carnot efficiency. It'll probably be something like 15 to 20%, whereas this case it was only 1.6% because the temperatures were too close to each other. The greater the difference between the hot reservoir and the colder reservoir, the more efficient your engine will run. Okay? Thank you.